slight discussions, locations of neutral axis. So if, for example, we consider this cross-section, and apparently this cross-section, this is for the plane of symmetry. And the reason why is this: once we can observe the plane of symmetry, then that axis actually serves as the principal axis. And in this way, the other principal axis usually is normal to this case. So here, that is the other one. So here, the two are the principal axis. Okay, the first step, we have to identify the principal axis on which any given orientation of the strain of the moment will be decomposed. For example, here we are given is M, moment in these unsymmetric bending locations. So the step is we decompose into the two components and onto the principal axis. So here it really depends on how you define your coordinate systems. And for example, let me follow up our textbook notation. This is Z, this is Y. And that's the reason why, and it depends on how we use our symbols for the coordinate systems, then you might have a different expression of the formula. So I don't recommend to memorize the textbook formula, but we can work on this kind of symbolically. And for example, here, let me define this angle is theta. Okay. So we have these conditions, and then we consider for a point YZ, because right now we have identified the coordinate system like this. This is like this, so we have the coordinates like this. For any point on the cross sections, the stress will be equal to. Right now, using this as the example, we do the symbolic calculation and by repeating the step like this. Okay, so look at this carefully. In terms of the sign, in terms of the direction like this one, we can see, if you wish, we can put into the two subsystems. Let me put into here. So one is MZ plus one is MY. Okay, we'll do this carefully. And in terms of the coordinate systems, and you can see, okay, let me divide into this one. So here, again, the upper will be in compression, the lower will be in tension. Let me identify those things first. So for this case, this will be in tension, this will be in compression. Okay, now we go on to this. So this will be the summation of the corresponding the two terms here. And for this case, this is MZ. And multiply the distance to the neutral axis. For this case, the distance to the neutral axis the distance to the z-axis is how much? Is the coordinate y. Okay? And divided by iz. Let me label this carefully. So this is neutral axis. This representing, right now this one representing is the magnitude. And then I want to determine the attribute. And look at this carefully here. In the lower quadrants, which is negative y coordinates, give us the positive stress. For any negative y coordinates, the whole thing must be positive. So here we must artificially add 1 minus sign. Okay?
So is it just absolute value of y?
Yes, making the whole things being consistent with the things. And one more time, for any point on the upper quadrant which has the positive y value, for positive y value, the stress whole thing must be negative. So here we know we must have a negative sign here. Okay. So right now for this example, we totally work on the symbols, and for generic any point, the same thing we're back to here. The magnitude of the moment is my respect to the neutral axis, and which is the y-axis. Okay, now we come to here. And this representing is the distance from the point to the y-axis, and which is z coordinate, right? And now we justify the sign. Look at here, for all the z coordinates, and per our sign convention, the z point to that way. So for all the positive z coordinates, that means lying on this quadrant. So for all the positive z coordinates, that the whole thing, the stress must be positive. So look at here, for the positive z coordinate, the whole thing automatically already is positive. So here we delete it without any additional sign. Okay? Okay. And now, if for the neutral axis, simply is asking stress equal to 0. So here that is mz over y minus divided by iz plus my over z divided by iy. So from here we can see the y over z, do this carefully, is my, mz, iz, iy. Okay, and my over mz, basically here is this. You can see the this amount is my, and this amount is mz. So basically that one can be related to the tangent theta and iz, iy. Okay, so you can see y over z. What is means y over z, and for example so here, the slope, right? So for example, this point here, and this point has the coordinate y and has the coordinate z here. So y over z simply represent is the slope. Right? So basically this one representing, let me say this is the neutral axis, and say this angle is phi. So simply this one is tangent phi. The phi representing is the orientation of the neutral axis, and equal to tangent theta and iz, iy. This is a formula in textbook. I don't think this is a formula. You can see to arrive to this, to reach this result, which depends on a lot of things. If I would change my coordinate systems, everything will be different. Okay, so I would say this one would be the regular, more generic exercise like we have here. Okay, but sometimes this could be a good foundation for certain things. But I won't recommend you memorize this one. Everything just starts from the beginning. So you might ask me, people ask me a lot of the same question, the following questions in ES331. It's saying when the direction of the n will align to the neutral axis. When? And right now you could answer these questions by using this result. When I is equal to Iy. Only in that condition. So usually in squared cross section, that could be one example. And for others, we need to kind of play around the dimensions to make that happen.